Welcome to AI Paper Slop. We're skipping the pleasantries today because we have a massive stack of research notes on a paper called Recursive Synthetic Terminal Tasks, or RST.
Right, which was published by researchers at Tencent alongside several universities.
Yeah, and our mission for this deep dive into the source material is to figure out how this team just absolutely crashed the cost of AI agent training data. I mean, they took it from hundreds of dollars down to roughly 5 cents a pop.
Which is just wild, 5 cents.
It's insane. If you build or train or even theorize about AI agents, you already know that getting verifiable long horizon training data for terminal agents is, well, it's the single biggest bottleneck in the field right now.
Oh, absolutely.
But this RST framework, it recursively synthesized over 37,000 highly complex, completely verifiable terminal tasks, and it did this with 0 humans in the loop.
0.
And the difficulty scales so exponentially over 15 rounds of mutation that a model like DeepSeek V4 Pro goes from a 90% pass rate and just crashes down to 2.5%.
It just falls off a cliff.
Right. But when they trained Quinn models on these generated trajectories using supervised fine-tuning and agentic proximal policy optimization, the model saw massive leaps, like a 41.2% relative gain on the brutally hard terminal bench hard data set.
Yeah, this paper basically rewrites the entire economics of synthetic data generation.
Yeah.
Because to fully grasp why that 5-cent metric is such a paradigm shift, you kind of have to look at why terminal task data was so painfully expensive to produce in the first place.
Right, because you can't just ask an LLM to do it.
Exactly. When you're training a language model to act as like a software engineer interacting with an operating system, you can't just prompt it with write a complex bash task.
Yeah.
It doesn't work. A valid terminal task relies on this highly fragile 4-part dependency.
Okay, 4 parts. Break that down for us.
Sure. So first, you need the public instruction, right? That's the text prompt given to the agent. Then you need the initial workspace.
So like the files in the OS state.
Yeah, the files, the dependencies inside the container, all of that.
Yeah.
Third is the reference solution, which is the actual sequence of bash or Python commands that executes the fix.
Yeah.
And finally, you need the private verifier.
The background tests.
Exactly. The hidden tests that evaluate if the final environment state actually satisfies the original goal.
So those 4 elements, they have to be in perfect mathematical alignment. It's a lot like building a fully automated escape room.
Right, like that. Yeah, an escape room.
Because if you're the designer and you decide to change one padlock in the room, which I guess represents updating the workspace environment, you have to perfectly rewrite the clue you hand the player. That's your instruction.
Right.
You also have to update the master key you keep in the back office, which is the reference solution. And crucially, you have to rewire the hidden sensors in the door that trigger the win condition, the verifier.
Yes.
And if an LLM hallucinates and just forgets to update even one of those components,
The escape room becomes mathematically unsolvable.
right.
It's broken. And direct generation from a language model almost always breaks that exact alignment. Like, a model might generate this brilliant verifier script that checks for a specific error log, but it completely forgets to tell the agent to generate that log in the public instruction.
Oh, right. So the agent is flying blind.
Totally blind. Or it writes a reference solution that relies on a specific tool, like JQ to parse JSON, but it just fails to include JKey in the environment's Docker file.
And the moment one of those dependencies breaks, the task is dead.
Dead on arrival. It's completely useless for training an agent. So historically, the only way to guarantee that alignment was to have human software engineers manually author and test all 4 components across thousands of edge cases.
Which simply does not scale. You can't pay engineers to write thousands of these manually.
Not if you want a massive data set, no.
Okay, so if prompting an LLM directly fails to keep our escape room consistent, how does this RST framework actually solve the puzzle?
Well, the authors introduce a mechanism they call solution-first recursive synthesis.
Solution first.
Yeah. It starts with a bootstrap pool of 639 highly verified seed tasks from a dataset called Terminal World. So these are known, solvable baseline tasks.
Okay.
And rather than trying to generate a harder prompt and just sort of hoping the code matches,
Yeah.
RST reverses the flow. The system scans a seed task and selects one of 40 specific rewrite operators.
What kind of operators?
They're categorized into 5 families, so things like file system and resource binding, or runtime and diagnostics.
Got it.
Let's say the system selects an operator that's designed to introduce a configuration inconsistency. The framework forces the LLM to expand the reference solution first. It writes new executable bash code to handle the broken config file, layering this new logic right on top of the original solution path.
Wait, I have to pause here because generating the underlying solution first and then building the test and the public prompt around what the solution did, that feels completely backward from standard software engineering.
It is backward, yeah.
Right, because we're all taught test-driven development, TDD, you write the requirement, you write the test, and then you write the code to pass the test.
Exactly.
So if RSK reverses this process, it seems like you were basically begging the system to create secret hidden requirements. I mean, the model could just go rogue, write a bunch of obscure bash scripts, and the agent is supposed to magically guess what the prompt was supposed to be.
You're spot on, and the authors anticipated that exact risk, which is why the synthesis relies on this really rigorous two-stage validation pipeline to guarantee the contract is fair.
Okay, how's that work?
Stage 1 is Oracle validity. So the newly expanded reference solution is physically executed inside a fresh Daytona sandbox.
A Daytona sandbox?
Yeah, it's a secure, isolated container environment. If the code crashes or if the environment doesn't even support the requested commands, the task is flagged for a bounded repair loop or it's just discarded entirely. Basically, the escape room has to be physically beatable by the master key.
Okay, so Oracle validity proves the actions technically work. But how do you enforce that the agent actually knows it's supposed to take those actions?
That's stage 2, contract validity. The framework runs a combination of static analysis and LLM-based verification to audit the workspace.
Okay.
It checks that every single requirement evaluated by the verifier is either explicitly stated in the public instruction or logically discoverable by an agent exploring the environment.
Oh, I see.
For instance, if the new verifier asserts that a web server is running on port 8080, the public instruction must either explicitly say start the server on port 8080, or it can say start the server using the default configuration. But only if the static analysis proves there is a readable config file in the workspace that clearly specifies port 8080.
Oh, wow. So if a requirement is neither publicly stated nor logically discoverable in the file system, the task is just rejected.
Exactly. The solution dictates the actions, but the validation pipeline guarantees the contract is fair and actually solvable.
Okay, so once a task passes both Oracle and contract validation, it gets dropped back into the seed pool for the next round of synthesis.
Yeah, it goes back in.
And they loop this process 15 times, right? Injecting new complications layer by layer. But we have to look at whether this actually makes the tasks strategically harder or if it just creates, like, bloated administrative busywork for the model.
Well, the progression from round 1 to round 15 represents a fundamental explosion in executable complexity. Just look at the numbers. In round 1, the median reference solution across the dataset is 67 lines of code.
Okay, pretty standard.
By round 15, the median solution is 374 lines of code.
Jeez.
And the number of discrete command executions required to solve the task jumps from an average of 40 to 244.
Executing 244 distinct terminal commands to solve a single prompt is a massive workflow. I mean, that requires serious persistence from an agent.
It does. There's this one case study in the paper that traces the lineage of a JSON diff regression task, and it makes this growth incredibly concrete.
Okay, walk us through it.
So it begins as a simple bootstrap seed, just a basic 10-line script where the agent is instructed to run a command line tool to generate a diff report comparing two fixed JSON files.
Right, that's like a standard entry-level CI/CD pipeline check. Super easy.
Very easy. But by round 1 of the synthesis, the rewrite operator moves the matrix of comparisons into a configuration file. So now the agent has to locate and read the config, batch run the comparisons dynamically, and write out a validation report. The required solution grows to 66 lines.
Okay, still manageable.
Fast forward to round 5, the system injects an operator that intentionally breaks the configuration.
Oh, brutal.
Yeah. So the agent must now run a checker, interpret the resulting stack trace, fix the JSON task list, rerun the test suite, and aggregate the counts. Now we are up to 219 lines of solution code.
So it's forcing the agent to perform actual forensic debugging rather than just executing a happy path script.
Exactly. And then by round 10, the synthesis agent has to parse a markdown file to discover a new nested fixture requirement.
Oh my God.
And by round 15, the workflow is just staggering. The agent is diagnosing inconsistent configuration and fixture data. It's fixing broken JSON files scattered all across the workspace, regenerating every diff report, writing a forensic diagnosis, reconciling expected diff counts, and finally successfully passing a full project test suite.
And the verified solution is how long?
347 lines long.
See, what stands out to me in that JSON progression is the divergence between the instruction length and the solution length.
Right.
Because the executable work, the solution lines, grew by 5.6 times, but the public instruction length only grew by 1.4 times, going from like 85 words to just 122 words.
Which is such an important distinction.
Yeah, the difficulty isn't scaling because the model has to read a massive novel-length prompt. The difficulty scales purely from having to navigate the environment, diagnose break-in states, and adapt to system feedback.
And that environmental complexity brutally impacts solver models. When they tested DeepSeek V4 Pro and they held the model architecture constant here, just evaluating its performance across the different synthesis rounds, the pass-at-4 rate, meaning the model solved the task within 4 attempts, was 90% on the round 1 tasks.
Okay, so it crushed round 1.
But by round 15, that pass rate plummeted to an abysmal 2.5%.
Which is wild. But I have to push back here. If a state-of-the-art reasoning model like DeepSeek V4 Pro is failing 97.5% of the time, the immediate assumption has to be that the pipeline simply degraded.
You'd think so, yeah.
Right. Like, if nobody can solve the escape room by round 15, the locks are probably just jammed. We're just generating broken, impossible tasks at that point.
But the Oracle validation proves the locks aren't jammed. Every single one of those round 15 tasks was executed and proven to be 100% solvable in the Daytona sandbox by the synthesized reference solution.
But the keys do work.
The keys work perfectly. The sequence of deductions required to find those keys has simply exceeded the current reasoning horizon of the solver model. Basically, the generator has successfully outsmarted the solver.
Wow. Okay, but wait. If you are iteratively self-improving on the exact same 639 seeds, 15 generations deep, the standard expectation is that the dataset will eventually cannibalize itself.
Mode collapse.
Yes, mode collapse. You should hit a wall where the pipeline either stops producing valid tasks entirely or it just converges into generating like 37,000 highly specific, bizarre JSON parsers that all look identical.
Right. Mode collapse is the bane of almost every synthetic data pipeline, but the RST framework completely avoids it.
How?
Well, throughout all 15 rounds, there is no observed ceiling or collapse. The synthesis yield, which is the number of accepted valid tasks generated per 1,000 attempts, remained highly stable. It hovered right around 530 accepted tasks from round 1 all the way to round 15.
That's incredibly consistent.
And the domain diversity of the tasks remained vast. The normalized entropy of the task categories barely shifted, moving from 0.821 in the seed pool to 0.817 in round 15.
Okay, so maintaining that level of entropy means the distribution of the data stays wide. It's similar to applying strict evolutionary constraints to prevent inbreeding within a population.
That's a great way to think about it.
But how does the framework actually enforce that computationally?
It uses strict diversity caps, modeled essentially as a directed acyclic graph, or DAG.
DAG, okay.
Yeah, so every task is a node, and the system tracks the complete lineage of every generated task. If a specific node, let's say it's a Python script debugging task, is very easy for the LLM to mutate, it might generate 5 valid children in a single round.
Right, because the model favors the easy path.
Exactly.
Yeah.
But the framework applies a hard cap to the parent lineage. Once a node hits its budget, the algorithm physically cuts it off. It just refuses to select it or its direct children for further mutation until the rest of the tree catches up.
Ugh. So by artificially throttling the successful branches, it forces the LLM to go back and figure out how to mutate the harder, less explored seeds.
You got it. And it applies those same hard limits to the task categories and the rewrite families. The framework physically forces the LLM to diversify its mutation strategy, which is actually why 36 out of the 40 rewrite operators were still actively being injected into tasks during round 15.
So the mutation mechanism is computationally blocked from settling into a rut.
Exactly.
So we arrive at the ultimate payoff. We have this data set of 37,484 perfectly verified, computationally diverse, brutally difficult terminal tasks that cost essentially nothing to produce.
5 cents.
5 cents. The critical question for anyone building models, though, is what actually happens to the policy network when we train an agent on this data.
Right. What's the actual result?
Yeah. And the authors break this down into 2 training dynamics using the Qwen 3.5 architectures. First, they tackle supervised fine-tuning, or SFT, using rejection-sampled trajectories.
And rejection sampling is a vital filtering step here. During the generation phase, the solver model might take multiple attempts to complete a synthetic task, right?
Sure, it fails a few times first.
Rejection sampling means the framework throws away all those failed rollouts and only keeps the successful optimal path through the environment. So they take those clean, successful trajectories and they fine-tune both the Quen 3.5, 27 billion, and 122 billion parameter models.
But by training only on the successes, you're essentially performing behavioral cloning. You're teaching the model how to solve the complex task, but you aren't necessarily teaching it how to recover when it makes its own mistakes in the wild.
That's the limitation of SFT. Yeah.
Even so, did the SFT phase scale effectively across the different model sizes?
It scaled monotonically. As they introduced data from the deeper synthesis rounds into the SFT mix, both the 27B and 122B models saw steady, consistent performance gains across Terminal Bench 2, Terminal Bench Hard, and the Long Horizon Terminal Bench, or LHTB.
Okay, so that confirms the synthetic data provides a robust signal that scales up to massive architectures.
Yes.
But while SFT establishes the baseline capability, the real frontier for agentic AI right now is reinforcement learning. So when they transition from behavioral cloning to applying PPO proximal policy optimization, how did the model's behavior change?
Well, PPO is where the agent truly learns resilience. Because unlike SFT, where the model only sees perfect solutions, PPO allows the agent to generate its own rollouts in the environment, make mistakes, and actually learn from them.
Because the reward signal is tied directly to passing the private verifier, right?
Exactly. And during the PPO training phase on the 27 billion parameter model, the mean verifier reward climbed steadily. But the most revealing metric to me was the trajectory length. The mean number of turns per trajectory grew from roughly 19 turns at the beginning of PPO to over 30 turns by the end.
And a turn being an action the agent takes and the observation it gets back from the terminal.
Right.
So instead of the agent hitting an unexpected system error, getting confused, and just giving up and terminating the run, it learns to dig.
Yes. It runs a command, gets an error stack trace, reads the trace, checks the directory for a missing file, writes a patch, and tries again. It learns to sustain long horizon interaction.
That's incredible.
The PPO phase optimizes the model's policy to value persistence and exploration, and that yielded incredible final results. For the 27B model, PPO drove a 20% relative gain on Terminal Bench 2, a 21.9% relative gain on LHTB, and an absolutely massive 41.2% relative gain on Terminal Bench Hard.
Okay, we have to scrutinize that 41.2% jump on Terminal Bench Hard.
Naturally.
Because whenever a paper claims a 40% jump on a benchmark, the immediate cynical reaction from the ML community is going to be data contamination.
Did it memorize the test?
Right. Did the model just accidentally train on the test set? But the authors address this head-on because Terminal Bench Hard was constructed entirely independently of the RST data. It was drawn instead from Tmax 15K.
But they go a step further and mathematically audit the data using unigram Jensen-Shannon divergence and 5-gram Jacquard similarity.
Okay, for those of us listening who haven't opened a statistics textbook recently, we need to ground those terms. What is unigram Jensen-Shannon divergence?
So the Jensen-Shannon divergence, or JSD, measures the overall probability distribution of the vocabulary between two data sets. It basically checks if the synthetic data just mimics the general vibe or linguistic structure of the benchmark.
Okay.
And the authors found that as the synthesis progressed from round 1 to round 15, the JSD actually increased, meaning the synthetic training data grew more distinct from the benchmark over time.
Oh, interesting. And what about the 5-gram Jacquard similarity?
Jacquard similarity is essentially a literal plagiarism checker.
Yeah.
It scans for exact copy-pasted sequences of 5 words overlapping between the training data and the final exam. The maximum 5-gram Jacquard similarity between the RST synthetic tasks and Terminal Bench Hard was below 0.009.
So it was practically zero.
Practically zero, yeah.
Yeah.
So by measuring both the structural divergence and the literal string overlap, they mathematically proved there is zero data contamination. That 41.2% performance gain is not the result of the agent memorizing the formatting of the RST tasks.
No, the agent genuinely learned how to generalize complex, multi-step terminal workflows.
It learned how to act like a systems engineer facing a novel environment, which is exactly the capability we're all chasing with agentic RL.
Yep. It proves that you can bootstrap a highly capable generalized reasoning agent almost entirely from recursively synthesized low-cost data.
Which really brings us back to the sheer economics of what this Tencent team has accomplished. For 5 cents a task, they have fully automated the creation of verified long-horizon environments that force models to develop deep, persistent problem-solving skills.
It's a huge step forward.
But there's a lingering thought I want to leave you with, one that isn't explicitly mapped out in the data, but is heavily implied by the trend lines here. We saw that there is literally no observed ceiling at 15 rounds, right? The synthesis yield remains stable, The entropy remains diverse, and the computational difficulty scales exponentially. So if the mechanics hold, what happens at round 50 or round 100?
That is a terrifying and amazing question.
Right. Could this recursive synthesis eventually generate synthetic environments and dependency webs that actually outstrip the complexity of the real-world software engineering tasks human developers face today? We may be on the verge of automating the creation of digital environments that human engineers couldn't even navigate themselves just to provide these models with the proper workout.
It's a fascinating trajectory to consider.
It really is. Thank you for joining us for this deep dive into the source material. We will see you next time on AI Paperslap.